In this video, we're going to see how we can process some of the guitar sounds using Fourier transforms and basically get our feet wet in manipulating sound files and looking at their transform frequency domain aspects. This process would be identical whether it's a sound file or a signal that comes in from, say, a radio telescope or something that comes in from a mechanical device. It's simply easier to interpret if we're looking at sound files, at least to get started. So what we're going to do is our standard input here, and then we're going to add two libraries here. So Librosa, which deserves an accent, is a library that'll let us do some audio input and output easily. And then the IPython display is something that's going to let us play some sound files as well. What we're going to do is load in a sound file using that Librosa library. If you do not have it installed, you'll have to go through the pip install process or whatever local version you're using to install libraries for Python. But once you have it, there's a load function that'll, as you might imagine, load a data file. In this case here, it will load a WAV file. Now you'll need to figure out where your file is. Ours is in, I believe, of a directory and then in something called audio samples. There we go. And guitar D4. Again, just using the tab key to autocomplete where possible. That way you avoid having typos. So your directory and file name will be different. But if we run that, it runs and nothing obvious happens. Whenever I'm dealing with a new function like this, what I like to do is figure out what in the world I just got. So I would ask, what's the type of X? Ah, it's a NumPy array, so it's a big long array. How big is it? Let's get this a bit fancier. We're going to print the X length, and we're going to use the format command for that. So we're going to say, what's the length of X? But this will make a nice pretty statement in the output. And it says, the X length is 97,000 things long. All right, we'll keep the type in there just for thoroughness. And the other thing we have is SR, so let's look at the type of SR. And we'll need to print that as well. Oh, it's just an integer. Okay, well, let's print SR equals, and then we'll put SR in there. SR is 22,050. Okay. I learned this by diving into the documentation and having worked with CDs and things like that back in the day. SR is the sample rate. So, got a note here. SR equals the sample rate, and what we mean by that is equal to the number of samples per second. So when you're looking at audio files, you're literally sampling those at 22,000 times per second, or 22,000 hertz. 22,050 hertz. How does that help us? Well, it helps us in terms of developing and understanding what these values in X mean. So imagine every 1/22 thousandth of a second, we get a new X value. And how many X values do we have? We have 97,000. And if you do a quick math, 97 into 22 is around 4-ish. That's about a 4-second clip. If you play the WAV file outside of this IPython, you'll see it's about 4.5 seconds long. Let's just confirm that with some math, though, here. Confirm the sample length, the audio sample length. And all we're going to do here is take the length of X. We'll make it a nice print statement. Sound clip is seconds long. And what do we need to format in there? We need to format the length of X. So we said take how many samples we have, the 97,000, and we're going to divide that by how many hertz we've got in there, so 22,000. And if we run that, get rid of that last quote, and we should, there we go, get a nice number like 4.4 seconds long. Perfect. So what we have is a sequence of X's, and we know kind of something about the relationship to time. X on its own is just a bunch of numbers. Now we have a context attached to it. Let's get a plot up so we can actually see what's going on with this. So what we need is a plot. Let's do a plot. Let's make a new figure that's more wide, though. So we're going to use this fig size option. And let's go wide, so 14 and 5. I'm taking random, not random numbers here, but a large X and a smaller Y, just to make it look like it's going out in the horizontal axis. Just see what that looks like. And realizing the right options are passed as equal signs in there. There we go. So we have a figure, and what we're going to do is, let's just try plotting X first. So plt.plot X, And there's our graph of the 97,000 X values. And we can kind of see this is the wave mentioned in an earlier writing or video, but it's not time on the axis here. So we need to get some time values in there. Well, what we need to do is convert these indices to time values using that conversion factor of 22,050 samples per second. So what we're going to do is develop a T array to match X, and that's simply going to be a ranged value from 0 to the length of X, and that would just give us ordinarily 0 to 97,000 whatever. That's not really what we want. We want to divide that by, well, we want to divide it by the 22,000 or the sample ratio. So we're going to get the same numbers, just 1 to roughly 100,000. Let's say 100,000 to keep it simple. And then we're going to divide that by the sample rate, 22,000, and see what we get. Oh, we get an error. Right, because this is a Python list. If we're going to do math on it, though, we had better make it an array that NumPy knows about. So another round of brackets here. Build all those integers, put them into an array, and then when we have an array, we can divide by the sampling ratio. Then we get our T values, and then we can just move the plot command down a bit and say, no, it's not just X. We're going to plot T against X, like so. Now, if we take a look at the X-axis, we're in business. We have our 4.4 seconds. Everything's looking lovely. We just go one step further and add some labels. So time in seconds, and the Y label, something like pressure. It's a relative pressure, but whatever, close enough. So these are the sound waves that we're seeing. If we want to get a little fancy, we could just zoom in on, say, the first 1,000 samples. So we go to 0 to 1,000. Make sure you do it for both the X and the T's. And there we start seeing the fun stuff. And we also see that we zoomed in on the time frame as well. So we have the capabilities here. I'll actually save that as a separate plot command that we can reuse later. But going back to the original T and X, that's the main thing that we're driving with. All right. Next up, it would be helpful if we could actually hear this. So we've loaded a sound file, but in some sense, it's not sounds yet. It's just a bunch of data points that we know represent sounds. Let's try this out by using that Python library at the very top. It was the IPython display as IPD. So IPD has this lovely tool called audio. So it'll build a little audio thing, and you can look at the help menu for this. For us, it's enough to know how to use it once. Basically, we have to give it X, and then we also have to give it a rate, or a sampling rate, which is exactly what SR is. So we're going to give it this array, and then we're going to tell the audio player how quickly those samples are represented, which is exactly how we converted the raw array to this time frame. We run that, and now we can actually play it. Now we can hear a guitar string, I hope. Now, just for fun, because we can, you can also do some fun things by just reinterpreting that same data. So if we just go back to here and just say X is a list of data points that represent a sound wave to us, but without the information about the sampling rate, it's not a unique understanding of what it means. It's just these numbers that start high and oscillate and oscillate and oscillate and go down to and fade away eventually to zero-ish. What we can do is trade that up and put that back. We can maybe sample it twice the frequency. So I press Shift-Enter to make sure that this file here, or this tool, gets updated, and press play again. Oh, and we hear a higher note. What's happening is that we're interpreting these vibrations as happening faster, twice as fast, in fact. And so we get a higher pitch in our ears. You can also go the other direction and press Shift-Enter to run it, and then you've got a nice bass going on there. Okay, there. We've got a nice bass going on there. And what else can we do? We could go even lower. We could go down 2 octaves and get down to the low end of the piano there. Or we can even do other things, like get a different note completely. We could even totally mess it up. But don't forget to Shift-Enter first to actually update the interface. Yeah, we're playing with the tone there, the pitch. And then we're back to our original. This is the actual recording at the appropriate sampling rate. All right. So where do we want to go next? Well, we want to take this graph here, and again, just remembering that it's made up of very complicated mix of different frequency things happening. Well, actually, not that complicated. That's what we want to find out. It's actually a relatively simple collection of frequencies, even though the graph that results from it looks complicated. So let's see if we can tease that out. Now we are looking at Fourier transforms. So it behooves us to do something like look at Fourier transforms in our libraries here, and you're getting the fast tour this time around. There's a ton, oh my goodness, Fourier transforms are a thing. They're in any numerical software package you care to mention, and one of the things we're going to talk a little bit later about is the fast Fourier transform versus just the Fourier transform. For now, just know that if you're in a computer and doing Fourier transforms, FFT is what you want. So we're going to do a quick look up in the help here. And we're going to find out that not only is there a Fourier transform that takes or identifies frequencies for us, it is a non-trivial collection of tools. So here we are in the module NumPy FFT, and inside that there is another FFT or an IFFT or an FFT2, reals, Hermitians, background, like this. There's some reading here, and I highly recommend you do it. And oh yeah, this is one of the seminal papers. If you're, I know it says 1965, but computers and Fourier and signal processing, this is where it all began in practical purposes. It's a lovely paper. For us right now, it's enough to be able to say, let's do a standard FFT. We're going to standard Fourier transform and see what we get. So what we're going to do is look at what goes into an FFT, but not that FFT, because this is the library level FFT, and then the FFT after that is the actual command. And basically, you just give it some data. So for us, that's our X instead of an A, but one-dimensional discrete Fourier transform, sure, whatever. This will all be explained later on. We just needed to get some answers or some demonstrations first before I gave the context. Let us do an FFT on our X value, and we'll call the output Y. That was not super exciting. All right, let's just do a couple things again. Let's say what's the type of Y. We know X is an array, an NP array. Y is also an array. Well, good start. Let's take a look at the length of it. Oh, look, we get an array of exactly the same size back. Interesting. What else can we do with this? Well, we can actually look at the values. Let's take a look at Y from 0 to 10. Ah, this is where it gets interesting. And if you watch some of the earlier content, you should not be totally surprised by this. There are complex numbers hiding in this. The X array was just a list of real valued pressures. We could graph that and it made sense. The Y values are going to be complex numbers. And this is where we start getting the teaser, where we really need to take a step back and look at the math. So we're going to back out of this and do some on-paper stuff shortly. But I'd really like to see what this looks like now. It's 97,000 numbers, remember? Let's put prints all around all these guys so we can see them all at the same time. So we're talking about an array of 97,000 complex numbers just for this 4-second guitar clip. So how do we do that? Well, let's do naive first. Let's do a plot of just Y and see what happens. We get a message, a warning at the outset. Casting complex values to real discards the imagine. Oh, right, of course. We can't just print or plot complex numbers. It turns out, and we'll see again why this is practical going forward, that what we really want to do is plot the magnitude. So again, looking at these numbers, this is like a 0.35 plus a this is 0.35 plus another 0.35. That's a direction in the real and imaginary directions. We can do Pythagoras and get the length of that value. What we need is the np.absolute value. What that will do is gather the magnitude of every complex number in the array Y. So we're going to take our Y's, turn them into real numbers, just their lengths, and then we're going to plot that. And so, lo and behold, we see, in fact, 97 odd thousand elements. That's exactly what we expected. And there's some lovely symmetries happening here. It looks like we have what looks like a perfectly matched set of bunch of peaks here, bunch of peaks here. Is that a coincidence? Of course not. Now we're going to investigate what that means. And let's do one last thing here and just see if we zoom in a little bit. Ooh, this is nice. Let's go to 4,000. What we see here is some of those stuff, but then these just gorgeous looking little peaks. There's structure here. There's something going on. And arguably that is way simpler to look at than what we had before. This graph, super complicated. This graph of somehow the transformed thing, and for those who have even seen a couple of videos, frequencies are going to be what we find on this x-axis here. We are going to find out that there's relatively simple frequencies that make up this complicated looking pressure graph. And that's going to be the whole point of Fourier analysis, is to not the whole point. One of the major aspects of Fourier transforms and Fourier analysis is to take something that looks complicated like this and be able to translate it into a relatively small number of frequencies that are the building blocks. But before we can do that, we really need to explore what these complex numbers mean and what these numbers here should be if we're talking about frequencies. Right now, these are just index numbers, just like we started off with the x's. We went from 0 to 97,000. Okay, how do I interpret frequencies on this? And then can we identify the frequencies that are in the guitar string vibrations?